Intermolecular Forces in DNA by Pafnocius Salib. Intermolecular forces, or IMFs, are the attractive forces between different molecules. They determine the characteristics of these substances in the different states of matter. Two factors that affect IMFs are electronegativity and polar bonds. Electronegativity is an atom's ability to attract electrons in a chemical bond. Fluorine is the most electronegative of all atoms, and oxygen and nitrogen are also very electronegative. A polar bond is created when the difference in electronegativity between atoms bonded to each other makes the electrons drawn closer to one atom than another, making one atom partially positive and one partially negative. Molecules with these polar bonds are called polar molecules. The bond will always be polar until it is broken. The three main types of IMFs are hydrogen bonding, dipole-dipole interactions, and London dispersion forces. Hydrogen bonding occurs when molecules are made up of a hydrogen atom bonded to oxygen, nitrogen, or fluorine, all three of which are very electronegative. The electrons in the molecules are drawn away from the hydrogen to the electronegative atom, making the hydrogen partially positive and the electronegative atom partially negative, and creating a polar molecule. The hydrogen bonds are the bonds between these polar molecules. The partially positive hydrogens of one molecule are attracted to the partially negative fluorines, oxygens, or nitrogens of other molecules, and vice versa, and this attraction creates hydrogen bonds which are extremely strong. The second major IMF is a dipole-dipole interaction. In a dipole-dipole interaction, molecules become polar because the difference in electronegativity between atoms makes one region of the molecule partially negative and one region partially positive, hence the name dipole. The dipole-dipole interaction is the attraction between the partially positive region of one dipole and the partially negative region of another dipole. Dipole-dipole interactions are similar to hydrogen bonding. The difference, however, is that hydrogen bonding is always due to the polar bonds between hydrogen and fluorine, oxygen, or nitrogen. Dipole-dipole interactions, on the other hand, can be due to any other polar bonds. The third major IMF is London dispersion forces, or van der Waals forces. These forces are between nonpolar molecules and occur when atoms coming together causes those molecules to become dipoles. As we know, an atom's positively charged nucleus, made up of a neutron and positively charged protons, is surrounded by negatively charged electron. When atoms come together to form a molecule, the electrons in the electron cloud of one atom are pulled slightly to the protons of the other atom, and they repel the other atom's electrons to the other side. This makes one side of each atom partially positive and one side of each partially negative. More importantly, one side of the molecule itself becomes partially positive and another side partially negative. These dipoles are temporary. The London dispersion force is the attraction between the partially positive side of one molecule and the partially negative side of another. These are the most common IMFs, but they come and go as molecules move and their electrons shift. DNA is the building block of life. It is like an instruction manual that determines all the biological characteristics of a creature. It is made up of nucleotides, which are a combination of a phosphate group, a sugar group, and one of the 4 nitrogen bases that are found in DNA. These are adenine, cytosine, guanine, and thymine, each commonly abbreviated by the first letter. So what does DNA have to do with intermolecular forces? Well, these nitrogen bases interact and bond with each other through intermolecular forces, particularly hydrogen bonds. Through these hydrogen bonds, the bases connected to one strand of the DNA are connected to the bases on the other strand, forming the step-like structure between the two strands. These hydrogen bonds allow the DNA's instructions to be carried out. Additionally, since cytosine-guanine pairs have 3 hydrogen bonds while adenine-thymine pairs have only 2, areas of DNA with lots of cytosine-guanine pairs are more stable than other areas. In addition, nitrogen bases can be stacked on top of each other. The bases have several partially negative and partially positive regions, creating dipole-dipole interactions that help keep the stacking stable. Here are my sources. Thank you.